Sri Krishna Arts and Science College. In today's session, we are going to discuss about the topic equivalence relations. First, we should know what is a Cartesian product A cross B. Assume A is one set and B is another set. A cross B is defined as the set of all ordered pairs A comma B, where the first element A belongs to the first set A and the second element B belongs to the second set B. So now a relation R is a subset of the Cartesian product A cross A. With this note, let's move on to the topic equivalence relation. A relation R on a set is an equivalence relation if the following conditions are satisfied. First, R is reflexive. That is, every element of A is related with itself. So A, R, A, for all A belongs to A. The second condition, R is symmetric. That is, A related with B should imply B related with A for all A comma B taken from the base set A. The third condition, R is transitive. Assume A related with B, B related with C. These together should imply A is related with C for all the elements A, B, C taken from the base set A. If these conditions are satisfied by a relation R, we call R as an equivalence relation. So let's see problems under this concept. Give an example of a relation that is reflexive but neither symmetric nor transitive. So in this problem, we are going to define a relation which obeys reflexive property and it should not be symmetric and not transitive. Assume the base set A as 1, 2, 3. And also I am assuming a relation R as 1, 1, 1, 2, 2, 3, 2, 2, 3, 3. So if this is my relation R, let me show R is reflexive first. For all the elements 1, 2, 3 belonging to A, it should be related with itself. So 1 related with 1, 2 related with 2 and 3 related with 3. So as all the 3 elements are related with itself, here R becomes reflexive. But R is not symmetric because 1 related with 2, but 2 is not related with 1 in R. As this condition is not obeyed, R doesn't satisfy symmetric property. Likewise here also 2 is related with 3, but 3 is not related with 2. So here also R is not symmetric. R is also not transitive. If I assume 2 elements here, 1, 2, 2, 3, it should imply 1, 3 also belongs to R, but according to R, 1, 3 is not present, showing R doesn't satisfy transitive property. So now this is an example of a relation which is reflexive, not transitive, not symmetric. Second question. A relation R on the set of integers I is defined as A related with B if and only if the difference A minus B is divisible by a positive integer m. So how a relation R is defined on the set of integers I here? The difference A minus B is taken. If it is divisible by m, the elements A and B are related. This is how R is defined. So in this problem, we are going to show R is an equivalence relation. To show R as an equivalence relation, R should obey reflexive property, symmetric property and transitive property. So let's show first R is reflexive first. Any element belong to the set of integers, say for example 1, the difference 1 minus 1, 0 is always divisible by a positive integer m. So as 0 is divisible by any positive integer m, the element is related with itself according to the given condition. So A is related with A for any element taken from I. This is true for all elements belongs to the set of integers. So hence R satisfies reflexive property. Condition number 2, symmetric. Assume A is related with B. So if A is related with B, we have to show B is related with A. So starting with A related with B, according to the condition given in the question, the difference A minus B is divisible by M. This we know. What I am supposed to show is B minus A. B minus A in the sense, this can be written as minus of A minus B is also divisible by M. Come back again. For any integer taken from the integer set, the difference A minus A is 0 is divisible by positive integer M. So the element 0 is divisible by any positive integer M. A minus A is divisible by M. If this condition is obeyed, I say A related with A. So this is true for all the elements taken from I. Hence R is reflexive. Property number 2, R is symmetric. Assume A is related with B. We show B is related with A. If A is related with B, the difference is divisible by M according to the given condition. Consider this difference B minus A. So how this B minus A can be written? Take minus sign outside. So it is minus of A minus B. So it's already known this term, the difference A minus B. Consider this term B minus A, which can be written as minus of A minus B. This difference A minus B is already divisible by the positive integer M. Hence, minus of A minus B is also divisible by M. We know if 5 is divisible by 5, minus 5 is also divisible by 5. Hence, the difference B minus A is also divisible by M. So, by the given condition, B is related with A. Hence, R becomes transitive. Hence, R becomes symmetric. The third, assume A related with B and B related with C. We try to show A is related with C. If A is related with B, the given condition gives the difference A minus B is divisible by M and the difference B minus C is also divisible by M. Hence, the sum is also divisible by M. So, on the set of integers I, if 2 is divisible by 2 and 4 is divisible by 2, the sum 2 plus 4 is also divisible by 2. Hence, A minus B, B minus C, the sum is also divisible by M. Showing A minus C is divisible by M, or by the question condition A is related with C. So, transitivity property holds. Now, we have shown R obeys reflexive property, symmetric property and transitive property. Altogether, we can say R is an equivalence relation. Now the next question. The relation R on the set of real numbers S is defined as A or B if and only if 1 plus AB is greater than 0. In the previous question, A is related with B if and only if the difference A minus B is divisible by M, that's given. In this question, how the elements A and B are related? Whenever this condition 1 plus AB is greater than 0 is satisfied. That's the only difference. If this is the relation R, we are supposed to show this relation is reflexive and symmetric, but this is not transitive. We'll go one by one. Let's show R obeys reflexive property. Assume any real number A. For any real number A, this term 1 plus A into A is always positive. Assume A as minus 1, which is a real number. Consider this 1 plus A into A, which is 1 plus minus 1 into minus 1. The total sum is 2. 2 is always positive. For any real number A taken from this S, this condition always holds. If the condition holds, the element A is related with B. So here the element A is A and A is B here. So A is related with A. For any real number A taken, hence R is reflexive. Condition number 2 now. Assume two elements from the set of real numbers S and A is related with B. We try to show B is related with A so that R becomes symmetric. If A is related with B, by the question condition, we have 1 plus A into B is greater than 0. On set of real numbers, the product A into B and B into A are equal. So A into B and B into A are equal. So replacing this AB by BA, I have 1 plus BA is greater than 0. So by the given condition, right here if A comes first and B comes next, A is related with B. So here B comes first, then comes A, hence B is related with A. So we started with A related with B. We prove B is related with A, hence R is symmetric relation. Now let's show a counter example for R, right, that doesn't obey transitive property. So we assume three real numbers from the set S as 1, minus 1 by 2 and minus 4. This is your A, this is B and this is C. So we can easily see A is related with B. So A related with B in the sense 1 plus A into B, the value is positive. So substitute A as 1, B as minus 1 by 2, check its value, it's greater than 0. So from the assumed AB, A is related with B. Now B related with C also can be checked easily. B related with C in the sense, this condition 1 plus B into C, that value is also positive. So now I try to show A is not related with C. So A is 1, C is minus 4 and the term 1 plus A into C, the value is minus 3. If it is greater than 0, A is related with C. As it is less than 0, they are not related. Showing R doesn't satisfy transitive property. So altogether R obeys reflexive, R obeys symmetric property, but R is not transitive. So this is a counter example where I can show the given relation doesn't obey transitive property. The next, if R and S are equivalence relations on a set A, then the intersection R intersection S is also an equivalence relation. If two equivalence relations are taken, the intersection is also an equivalence relation. This is what we are going to prove. So basically I have to start with a relation that's equivalent. So I have to show first the intersection set R intersection S is a relation. So given R is equivalent, S is equivalent. So R is a subset of the Cartesian product A cross A, S is a subset of A cross A. So as R is a subset of the Cartesian product and S is a subset of the Cartesian product, sure, the intersection is also a subset of the Cartesian product, showing this is basically a relation on A. Now let's try to prove this is an equivalent relation. Equivalence relation in the sense I am supposed to prove the first reflexive, the second symmetric and the third transitive. So assume an element belongs to A. We know as R is reflexive, A is related with itself and S is reflexive, A is related with itself. So the common element is present in R and S. Hence, A comma A belongs to the intersection R intersection S, showing R intersection S is reflexive. Second one, now try to prove R intersection S is symmetric. Start with A comma B belongs to R intersection S. So, if the element is present in the intersection set, it is present in R as well, it is present in S. So now R is equivalent. So R obeys symmetric property. If the element A is related with B, obviously B is related with A in R. Likewise, B is related with A in S. So joining these together, the element B is related with A in the intersection set R intersection S also. So started with AB belongs to R intersection S. We ended with BA belongs to R intersection S, showing this is a symmetric relation. Now let's see the third condition, transitivity. Assume two elements belongs to the intersection set R intersection S. So AB belongs to R intersection S, B comma C belongs to R intersection S. So from this, a common element is present in R, the element is present in S also. Likewise, B comma C belongs to R, B comma C belongs to S also. So we can split the elements like this. AB belongs to R, AB belongs to S. BC belongs to R and BC belongs to S. So now we try to combine the elements of R and combine the elements of S now. So AB belongs to R, BC belongs to R. As R is transitive, it implies AC belongs to R. The same, we combine the elements of S now. AB belongs to S, BC belongs to S, AC belongs to S because S is already transitive. So we have an element present in R as well as in S. The element is now present in the intersection set. So we started with AB belongs to R intersection S, BC belongs to R intersection S. We ended with AC belongs to R intersection S. So the property of transitivity holds. So R intersection S is transitive now. Showing altogether R intersection S is reflexive, symmetric and transitive. Hence R intersection S is a equivalence relation. So quick recap on this topic, equivalence relation. A relation is a subset of the Cartesian product. A relation is an equivalence relation whenever it satisfies reflexive property, symmetric property and transitive property. Thank you.